Hello and welcome to this International Society of Automation webinar. My name is Kim. I'm an Event Marketing Manager with IEEE Global Spec, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. You should be seeing the welcome slide there right now. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter, Scott Summer. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the Q&A window and click Submit. Your question will be placed in the queue for the speaker to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now allow me to introduce today's speaker and get this webinar started. Scott Summer is Life Sciences Program Manager with eTechnologies Group. Over to you, Scott.
Thank you very much, Kim. My name is Scott Summer, and I'm a senior member of ISA, the International Society of Automation. Just like IEEE, we are an organization dedicated to the development, education, and needs of our members. It is a real pleasure to be with you today and to cover the 5 skills that all automation engineers should master. Electrical engineers and other IEEE members are one of the largest groups of engineers that have chosen automation engineering as their career path. And I'm sure there are many others in the audience today who would like to explore a career in automation engineering. Here's a little bit about me, my family, hobbies, and ISA activities. On the professional front, I'm a licensed professional engineer and a certified automation professional. Both credentials have served me well in my career, and I'm fortunate to have been able to obtain them both. So let's get started with the first concept that all automation engineers should master: understanding the science behind the 4 to 20 milliamp current loop. Electrical engineers will probably not be overly impressed nor overwhelmed by the complexity of this circuit, but it does form the basis for all analog inputs and outputs to the process control system, and it does have some unique properties which make it ideal for use in control systems. Whether we use a PLC, which is a programmable logic controller, or a DCS, which is a distributed control system, the current loop is used to convey analog information from the field instrument, such as the differential pressure transmitter shown here, to the control system represented by the device at the bottom of this diagram. PLC and DCS analog inputs and outputs are powered by a 24-volt DC source. Other devices, such as remote displays or chart recorders, could be added in series to the loop, but this is not usually done. The usual way that current loops are implemented in a process control system is with one transmitter and one analog input to the PLC. Sometimes 24-volt DC is provided by the control system, and sometimes it is provided by an external power supply. The analog input card at the I/O rack has an internal 250 ohm resistor, which converts the analog signal to a 1 to 5 volt DC signal at the analog input card. This is the ideal voltage range for the printed circuit components on the analog input or output card. Taking a closer look at the pressure transmitter I used in the 4 to 20 milliamp loop example, we see that the measurement, in this case pressure, is detected using a resistive bridge. This is one of the many technologies for sensing pressure. As with most transmitters, the sent signal is converted into a 4 to 20 milliamp signal. In addition, this transmitter is loop powered, meaning that the 24 volts DC circuit of the analog input can power the transmitter without an external 24 volt power supply. This circuit measures the signal from the resistive bridge pressure sensor, which is excited by a 5 volt reference, which you see at the top. An instrumentation amplifier gains up the sensor signal, which is converted to a current by resistor R1, and is then summed with an offset current generated through resistor R2. This current flows through resistor R3 and is amplified via the op-amp configuration that is shown, and then through resistor 4 to form the 4 to 20 milliamp output. Because the current consumed by the entire transmitter returns through resistor R4, it is included in the regulated 4 to 20 milliamp current. Thus, the loop is loop powered. You should be beginning to see that there is a great deal of electrical engineering knowledge that is helpful to understand even simple current loops. In this slide, we see that placing multiple devices on a single current loop is possible, but the secondary devices to the transmitter should have very high impedances in order not to alter the overall loop resistance. Here, a chart recorder and a remote display, both with impedances of 200 kiloohms in parallel with our transmitter, will affect the loop resistance by only about 0.25%. Another really cool feature of the 4 to 20 milliamp circuit is that it is possible to overlay a digital signal on top of the 24-volt DC current loop, thus providing additional data capacity and capability in the transmitter. When we superimpose a Bell 202 modem 24-volt AC frequency shift keying signal on top of the current loop, we can access configuration parameters, store tag names, trim the sensor output, and change the range of the transmitter from a remote location. We can communicate using this digital protocol, which is called HART, H-A-R-T, from anywhere that we can clamp onto the circuit with a handheld or PC-based configuration terminal, whether it is at the transmitter, in a junction box, or in the control system I/O panel. This allows us to service the transmitter without having to be in a hazardous, hot, wet, or other restricted environment. Here are some more fun facts about HART. The two things to take away from this slide is that the digital signal is a 24-volt AC, frequency-shifted sine wave that does not alter the DC signal since the amplitude of the sine wave above and below 0 volts is the same. The second takeaway is that the same wiring can be used as a normal 4 to 20 milliamp current loop, so wiring does not need to be changed if you upgrade a loop with HART. However, both the transmitter and the analog input card in that case must be HART capable. So let's move on to the second concept every automation engineer should master, and that is knowing how to calibrate an analog transmitter. The differential pressure transmitter we used in the current loop discussion will look very much like the one shown here, regardless of the manufacturer. The process pressure is applied to the face of the isolation diagram via a process connection, such as a 1.5-inch flange. Notice that the sensing diaphragm, when it is pressed upon by the isolating diaphragm, thereby moving the sensing diaphragm relative to the capacitor plates in the sensor. The silicon oil between the isolating diaphragm and the sensing diaphragm allows the pressure signal to be transferred to the sensing diaphragm. As the distance between the sensing diaphragm and the capacitor plates changes, a small electrical potential is developed across the lead wires, according to Faraday's law. This type of pressure transmitter is called the capacitive pressure transmitter. Also note that the zero and span adjustment screws on the face of the transmitter. These will be used to calibrate the sensor, and we will discuss calibration just a little bit later. Now let's look at the measurement error. When transmitter senses a measurement such as pressure, there's invariably some degree of error in the measurement. Measurement error is the algebraic difference between the indication at the transmitter and the actual value of the measured variable. As you can see, there are 4 types of measurement error: zero error, span error, linearization error, or a combination of all of the above. Zero error is simply an error characterized by a constant offset over the entire measurement range. There can be positive or negative zero error. Zero error can be corrected by calibration. Span error is an error that has no zero offset, but increasingly deviates from the true measurement over the range of measurements from 0 to 100%. There can be low or high span error. Span error can usually be corrected by calibration as well. Linearity errors exhibit the behavior shown here. This type of error is usually due to physical damage to the transmitter and usually cannot be corrected by calibration. Replacement or repair of the transmitter or correcting installation issues may be the only options. Calibration is simply the adjustment or set of adjustments that are performed on an instrument to make the instrument function as accurately or error-free as possible. As is shown here, good control of the process is only possible with accurate measurements, and accurate measurements are only possible with proper calibration of the instruments. To calibrate, a process or simulated signal is sent to the transmitter, and the resulting output, 4 to 20 milliamps, is observed. When the input signal is set to the minimum, or 0% of the range, the output signal should be 4 milliamps. At 100% of range, the output signal should be 20 milliamps. Making the preceding block diagram just a little bit more real, we see that a very accurate process simulator, in this case a pressure supply, is connected to the process side of the transmitter. A current meter is attached to the output to measure the transmitter's 4 to 20 milliamp output. Ideally, we would use an NIST calibrated simulator and current meter. In practice, we can use very accurate Fluke or AmProbe process meters and pressure modules as our sources of pressure and measurement of milliamps. The ISA standard is to use what we call a 5-point calibration, meaning the transmitter is tested at 0, 25, 50, 75, and 100% of measurement range. The test should be performed traveling from 0 to 100% and then going backwards from 100% to 0. This dual direction calibration helps detect any hysteresis errors or lack of repeatability. Here's an example of a completed calibration chart. This shows the ideal and measured values for each percent of input of span we use in the calibration. We always take the values from 0 to 100% as we find the transmitter prior to making any adjustments. One common mistake is that an attempt is made to calibrate an instrument already with an acceptable tolerance. The as-found values will allow us to determine if further calibration is required or whether we can save the effort and move to the next instrument. If a transmitter requires calibration, the zero and span for the transmitter can be adjusted to help reduce the measurement error. With our analog transmitter, we saw that there was a zero and span adjustment on the transmitter itself. Zero adjustment is made to move the output to exactly 4 milliamps when a 0% process measurement is applied to the transmitter. And the span adjustment is made to move the output to exactly 20 milliamps when a 100% measurement is applied. Unfortunately, with analog transmitters, the zero and span adjustments are what we call interactive. That is, adjusting one will affect the other. Therefore, the calibration is an iterative process to set zero and span, but usually 2 to 3 iterations is all that is required. Following calibration, the same data is collected by applying 0, 25, 50, and 100% to the transmitter's process input. The transmitter outputs are recorded at each value as before. If you take a quick look at the last 2 columns, it's quite apparent that an improvement has been made by making this calibration. Once the as-found measurements were taken, we can graph the results as percent of error. Here we see that the maximum deviation observed was about 0.25%. If you look back at the chart on the previous slide, you'll see that that's the case. This graph shows the upscale and downscale values with some degree of hysteresis evident. If the accuracy tolerance limit is 0.5% for our transmitter, we see the transmitter is well within the tolerance and no recalibration is necessary. However, if the accuracy tolerance limit, on the other hand, is 0.2%, then recalibration will be required. After calibration, the errors are graphed once again. As with the as-found values, there is some degree of hysteresis. However, the maximum deviation has been reduced from about 0.25% to about 0.1%, well within the tolerance of plus or minus 0.2%. If we have an analog transmitter, we must adjust zero and span to reduce the measurement error. As we saw previously, these adjustments are interactive. With a smart transmitter, like a Hart transmitter, we can take advantage of the analog to digital and digital analog converter properties to calibrate the transmitter. With a digital transmitter, we can adjust the incoming sensor signal by adjusting the A to D converter output, which is called sensor trim. And we could also adjust the input to the D to A converter in the output circuit, which is called 4 to 20 milliamp trim, or simply output trim. Both of these adjustments help us to adjust the output signal from 4 to 20 milliamps to correctly match the 0 to 100% range of inputs. Now let's move on to concept 3, which is that every automation engineer should master is how to tune simple and complex control loops. This is the generic model for a feedback control loop. The process variable, our measured or transmitted variable, is brought into the controller and compared to a set point. The difference between the set point and process variable, which is called error, is used in a controller algorithm to determine the amount of change required to the position of the final control element in order to bring the process variable back to match the set point. Final control elements are typically control valves, variable frequency drives, or dampers. As shown on a process and instrumentation diagram, or P&ID, this temperature control loop is comprised of a temperature measurement, a temperature controller, and a control valve which is used to control the water flow to the cooler. The cooler represented on the P&ID is a shell and tube heat exchanger. We can observe that if a process is at steady state, we can change the valve output by a known amount, and then we can use the resultant change in the process variable to determine some important properties of the process. In automation, we assume that most processes follow what we call a first-order process with dead time model, which is easy to describe as a first-order mathematical equation. Higher-order processes are much more difficult and require computers and other computational devices. For instance, in the graph here, a flow control valve may have been opened an additional 10%, which is our set point or manual change shown on the left, resulting in an increase in the flow rate from an initial steady state value to a new steady state value. This value does not respond instantaneously. It takes a little bit of time for the new steady state to be reached. The first property of the response curve is the time constant. Like I said before, the new steady state is not instantaneously reached. It takes a little bit of time. And we can describe that time as the variable tau, which is our time constant. This is the time it takes for the process to reach 63.2% of its new steady state value. In this diagram, we see that one process, the one on the left, reaches 63.2% of its new steady state within one time unit, whether that's in minutes, seconds, or whatever it happens to be. And the other process reaches 63.2% of its new steady state in 2 time units. Therefore, we can say that process 1 is faster to respond to the process bump of 10% than was process number 2. In this process, a fluid is being heated with steam. The measurement of temperature is being made a long distance from the control valve. Consequently, when a disturbance occurs, such as a control valve output change, it takes a period of time for the temperature to begin to increase. This is called dead time, and a large dead time makes control of our process quite a bit more challenging. Now let's complete the picture. We talked previously about the time constant, which is represented by the Greek letter tau. We represent dead time as the Greek letter theta, and we define a third value, k sub p, as the process gain. The process gain is simply the percentage change in the process variable divided by the percentage change in the output that created the process change. These are the reaction curve parameters for FOPDT, or first-order processes with dead time, a first-order process with dead time. We will use these parameters to calculate suitable tuning parameters for a feedback control loop. One important step in this method is to draw the steepest tangent to the reaction curve. Where the tangent crosses the original steady state line is the end of the dead time period. It's also where time equals 0 for determination of the time constant. Represented here is a block diagram of the equation that describes the ideal PID control algorithm. PID stands for proportional, integral, and derivative. The PID equation is used to determine how the final control element should change to move the process to the set point. The proportional action adjusts the valve output in response to the magnitude of the error on the current execution of the PID algorithm. Integral action adjusts the valve output in response to the integral of the measured error over time. In other words, the accumulated error over a period of time. Derivative action adjusts the valve output in response to the derivative of the measured error, or the rate of change of error, over the two successive executions of the PID algorithm. If we say variable m is the calculated valve output, we can describe equations for various control modes. These modes are combinations of the P, I, and D contributions, proportional, integral, and derivative. Most controllers are set up as PI controllers, or proportional plus integral controllers. Notice that there is no D only or control. That is because the Controllers cannot operate on the rate of change of air only. To set up or tune a controller, we first need to set a tuning parameter which adjusts the valve output using the proportional term. The tuning parameter for the proportional is called gain and is represented by Kc. For integral, the tuning parameter is called integral time, which is represented by T sub I and can be expressed either as minutes per repeat or repeats per minute. So in that definition, what is actually being repeated? Well, it is the proportional action. Therefore, proportional and integral actions always move the valve in the same direction. The derivative tuning parameter is the derivative time in seconds and is represented by T sub D. Using the values of process gain, Kp, time constant, tau, and dead time, theta, we can calculate the value of the tuning parameters for each combination of controller modes. These relationships were derived from mathematical treatment of the first-order process with dead time response model by two gentlemen, Ziegler and Nichols, both of whom were process control engineers prominent in the field from the late 1930s through the 1970s. Most modern digital controllers apply the PID control algorithm as shown. See, automation engineers and electrical engineers have quite a bit in common. Proportional action is determined with op-amps with variable gain. Integral is determined similarly with an integrating capacitive feedback circuit, and derivative is determined with a capacitive input circuit. Execution of the PID control algorithm in the controller should not be faster than the I/O update time, or the time it takes to update the inputs and outputs from the field. Otherwise, the PID algorithm will execute using a stale or old input data. PID control is designed to drive a process variable to the desired value or loop set point. The Ziegler-Nichols equation was designed to give control response that drives the process to the set point, following what is shown here as the compromise curve. This is characteristic of a well-tuned proportional integral and proportional integral derivative controller. The fast response curve gets the process to the set point more quickly, but a high gain and low integral time of a proportional integral controller can cause considerable overshoot. Loops that are integral dominant, like integral-only controllers, have a very damped response, like the curve identified as the slow response curve. The response curve referred to in the previous slide as the compromise curve is often referred to as quarter wave dampening, since the amplitude of each successive peak is 1/4 of the amplitude of the previous peak. This type of response is desirable because it gives minimum error integration with very good loop stability. Sometimes, as automation engineers, we do not have the luxury of doing a bump test on a valve output to determine the process reaction curve and the process dynamics. In those cases, we can use qualitative tuning maps to determine how the tuning parameters should be adjusted, especially for existing control loops. If we find that a control loop exhibits the response as shown in the graph in the first column, row 3, it shows that this particular response oscillates below the set point value. In this case, we will want to reduce the gain and increase the integral action to bring it into the reaction curve shown in column 2, row 2, which is very close to quarter wave dampening. Of course, the endpoint for your tuning is determined based on the engineer doing the tuning and the process response desired. Responses such as column 2, row 1, which shows a completely damped response that reaches set point after a period of time, may be the desired result, as in filling and bottling type operations. Normally, however, we want more of a quarter wave dampening response, which would be either the column 2 or 3 response, row 2. Often, a process does not exhibit first-order dynamics. In fact, in many cases, it does not. So control of the loop may have to depend upon the application of more advanced regulatory control approaches. Here we have a steam-heated exchanger that is subject to several disturbances. The steam flow and pressure can vary due to the boiler or steam header variation, which will make the enthalpy or heat flow into the exchanger also variable. With a steady feed flow, this would cause the temperature swing at the outlet. Also, it appears that the flow may also vary, so for a constant enthalpy flow into the exchanger, temperature fluctuations will also occur. One way to overcome this is to use a feed-forward control scheme, which is designed to control the disturbance, not the outlet temperature directly. We can use a familiar heat balance equation using the inlet flow W, heat capacity of the feed Cp, temperature difference between the set point and the incoming feed temperature, which is represented by T sub Sp minus T1, and enthalpy, delta H, in BTUs per pound of steam, in order to calculate the steam flow rate required in pounds per hour to heat the feed to the desired outlet temperature. Because of fouling, heat losses, measurement error, and the like, we can use feedback of the actual outlet temperature to adjust, or what we call trim, the control output in order to maintain the temperature at set point. But notice in feed forward, we are controlling according to an equation and not controlling the output temperature directly in a PID loop. This brings us to concept number 4, and that is how to design an Ethernet network for speed and reliability. Shown here is a typical network architecture for a process control system installation. There are 3 plant networks shown: Plant A, Plant B, and Plant C. According to the Industrial Automation and Control System Security Standard, ISA 99, the network should be designed so that equipment with like security requirements are grouped together in zones, which are shown by these red boxes. So Plant A supervisory LAN and the Plant A control system LAN will have similar security requirements within each of those zones. The communication paths are called conduits, as shown by the green boxes. ISA 99 prescribes approaches to protect each zone by placing a device on each conduit at the edge of a zone, such as a firewall or a router. So we should segment our plants into zones which have groups of PCs or other devices that have similar security requirements, and protect each zone by the use of a firewall, router, or other security device. There are several similarities between automation control system networks and the networks used in the office environment. For automation networks, downtime is not usually tolerable. Throughput speeds need to be very predictable, and tasks on the network, such as reading I/O values from an I/O rack, must be done on a scheduled basis, such as once every 250 milliseconds. The proprietary networking schemes of vendors in the past are now being replaced by standard cabling and protocols, and the best practices of IT are being employed wherever it makes sense. This and other topics will be covered in a future webinar in this series. Instrument buses, such as Foundation Field Bus and Profibus, allow clusters of instruments to be connected to the control system in efficient, reliable ways. The use of HART and other smart instrument technologies allows faster, more robust communication of sensor values, configuration data, and diagnostics back to the operator station. Ethernet is used extensively in automation because of its low cost, availability, robustness, and familiarity. Ethernet is a digital communication protocol which has a high throughput capability and reliability. 10 megabaud Ethernet uses a 1.2 volt peak-to-peak Manchester encoded signal. In this protocol, transitions in the signal on the clock ticks indicates either a 1 or a 0. A positive transition is considered a 0, and a negative transition on a talk click is considered a 1. This type of signal has excellent RF immunity and has built-in clocking. The more current 100 megabaud and gigabit Ethernet protocols use clock and transition schemes that are far too complex to illustrate here. This slide illustrates the full ISO model for communication protocols that was developed in the 1970s. On the left, you'll see an application that wants to send a piece of data to another computer. As the data passes down each of the 7 protocol stack layers, additional header information has to be added. This results in a very large packet of information that needs to be sent to the receiving computer. Most modern industrial protocols, however, including those based on Ethernet, use only the bottom 3 layers for communication. This improves speed and throughput since the number of overhead bytes is greatly reduced. In fact, in most modern Ethernet implementations in process control, the bottom 3 layers are actually combined into one single layer, further reducing the amount of overhead. Lastly, it is important to understand the concept of ports. Applications such as SMTP for use in email applications such as Outlook and HTTP used in web browsers such as Internet Explorer have defined port numbers in the operating system. One piece of data added in the message header is the sending port number. When the message is received by another computer, the port number is what indicates for which application in the receiver the message is intended. The use of distinct port numbers by various applications on a single computer is what makes concurrent execution of multiple applications possible. Port assignments also follow the applications and operating system to parse the data in the received packet. This is called demultiplexing, and it does so in a very fast and efficient manner. Port numbers 1 through 1026 are reserved for operating system use, and third-party applications use port numbers greater than 1026. And now we're to the final concept that every automation engineer should master, and that is how to effectively manage an automation project. Automation and control projects have some unique qualities that make them very challenging to manage. Rapidly changing technology may introduce major changes to a multi-year project during its lifetime. Other things like intangible deliverables, such as informal technology transfer to technicians during startup, and custom software development make automation projects unique and challenging. I apologize, I didn't have the slide up. Integration of systems into existing plant structures and business processes and heavy use of standards make project management an essential part of any large or small automation project. Automation and control work is usually done last, so it tends to get a disproportionate share of attention. Experienced automation engineers have witnessed the anxiety of the client as the project nears completion and automation owns all the remaining tasks in the critical path. I've been at that point more times than I can count. The ISA phase approach to project management and project execution is centered around the belief that sequential project phases allow the work to be managed and completed best when specific groups of tasks are completed prior to downstream tasks beginning. Some overlap in phases is expected, but the phased approach dictates what phases, the feasibility and definition phases, dictates that those be completed before the how phases are begun. This would include the basis of design. Once the basis of design is complete, the design freeze milestone becomes a signal to begin what we call the do phases, which include detailed design, testing, and construction. The relative size of the task blocks in this diagram are approximately in proportion to the size of the effort needed to complete each task. Finally, the Certified Automation Professional, or CAP model, is used to plan and track documentation, activities, and deliverables that should occur in each project phase. Proper planning, resource allocation, and tracking of individual tasks is essential to a successful automation project. Thank you very much for attending today's webinar and for your attention. Now let's get on to some questions and answers. If we don't get to your question during the time allotted, please note that the complete Q&A transcript, including answers we may not have had time to answer, will be posted with the webinar when it goes into on-demand mode. And without further ado, let's get to our first question. Let's see. One question that we have is, what feed-forward can be used in heat exchange only? If I am interpreting your question correctly, I would say that a heat exchanger is going to either have a cooling or a heating medium that are used to heat or cool the process stream. And the types of feed-forward or the implementation of feed-forward for steam would be either to control the flow of steam, like I illustrated previously, or you can control the steam pressure, which in practice I believe works much better. Again, the whole point with steam control is to maintain the correct amount of enthalpy delivery into the heat exchanger, whether you're controlling it to the outlet temperature with trim or without trim. So flow and pressure can both be used for steam or other heating methods. For cooling media, usually we just use the flow rate. Okay. When tuning loops, how many process states must we measure the response of the system? Or the response should be the same regarding system state, different pressures, temperatures, etc. Most loops can be tuned with one set of tuning parameters. Flow is one that is very much that same way. However, many types of loops do have different process reactions or process responses in different regions of your operation. For instance, we had a a pressure loop that actually had 4 distinct process reaction curves depending on which range of pressures we were looking at. So very often you need to come up with a scheme in your DCS or PLC that takes advantage of those different process regimes and actually adjust your tuning parameters based on where you are in your operation. Here's a great question. What advice would you have for someone just out of college and entering the automation field? There are many things that you can do. First of all, I would attend all the seminars and webinars that you can, such as this one, to learn as much as you can about automation. If you're in the automation field and just starting, then you want to find a mentor, somebody who has experienced in automation and can help guide you and more or less give you direction is what you need to know and how you need to or what information you need to obtain in order to succeed in automation. There's many resources from ISA. I would, just as a shameless plug, suggest that you join ISA because there are a lot of people in our organization that would be glad to mentor and help you in your quest to become a seasoned automation engineer. So educate yourself is the big thing. Find a mentor, and then set goals for yourself and try to achieve those. Goals. All right, another question came in. What are the best automation software available in instrumentation? So I'm not sure I quite understand the question, but there is a lot of software available, obviously, in automation for all different kinds of applications. On the instrumentation side, when we're dealing with bus instrumentation, there are some very good programs that can help you implement buses like Foundation Field Bus, Profibus PA, Profibus DP, DeviceNet, etc. What I would suggest, if you have a particular bus that you are interested in or dealing with, that you go to that organization that governs that particular protocol. For instance, you can go to profibus.org and get the information that you need on Profibus. They'll have a lot of suggestions for different software. Pactware is a program that's free. You can get it from many different vendors, and that is very useful for interfacing for most of these instrument bus type systems. As far as control software, there's just a whole host of PLC programming software, a whole host of HMI, human machine interface, or operator station software. And again, I would choose those based on your individual need and what the vendors are able to offer you. And especially around the world, we've seen that most people go with a company that is local, so they get good local support. All right, another good question about project management. How do you manage being on the critical path for automation projects with stakeholders and non-technical personnel? Well, when you're on the critical path, and pretty much every automation project is going to end up on the critical path because what we do just comes last in the progression of things that need to happen. So how do we deal with people who are stakeholders and non-technical personnel? First of all, you need to include those people in the development of the automation system from the beginning. Don't wait till after everything's done to find out who the stakeholders are or who the people who you need to interface with are at the business level or the quality level or warehousing folks. You want to make sure that up front in the project you identify all of the stockholders, including all of those non-technical personnel who are going to participate in the project. Make sure that they're part of the decision-making process, the information process where they would be on the distribution for documents and the such. So you want to include them. You want to make sure that you have a good relationship with them. And then when you get to the point of being on the critical path, then they can be your allies rather than those that are just tapping their fingers and stomping their feet. Okay, we have another question here. What general engineering major would you recommend taking for a career in automation engineering? I'm going to say any of them. I am a chemical engineer. In my organization, we have electrical, mechanical, industrial engineers. I don't think we have any geological or geotech engineers that are automation engineers, but I do know a couple. So most every engineering discipline is going to give you the basics that you need for a successful career in automation. You can always learn PLC programming. You can learn the simple electronics that we use in our transmitters and control systems like I just illustrated. But what you really need to come to the table with is a good understanding of thermodynamics, fluid flow, fluid dynamics. You need to come with a good understanding of mathematics, calculus, and the like, and have a good ability to solve problems, because a lot of what we do in automation is simply problem solving and then applying the tools that we have to solve those problems. Certain engineering disciplines may have a leg up, like chemical for process knowledge, but that's something that obviously can be learned. Electrical engineers would have more electronics and electrical knowledge, but certainly that can be learned. So any of the engineering disciplines are fine, except you want to make sure that you have that good mathematical foundation, good fluid dynamics and thermodynamics foundation, as well as good problem-solving skills. That's an excellent question. Here's another good question. How can we prevent interference in loop-powered 4 to 20 milliamp signal loops? One of the problems with DC-based circuits is that they're susceptible to interference or EMI that's developed by large conductors that are used for motors, AC currents, etc. So what we do is we ground the 4 to 20 milliamp cable at the control system end or the non-field end of the cable, wherever that cable is being connected to. We don't ground at the instrument, because if we grounded every instrument there, then we could typically form some pretty nasty ground loops, which I've witnessed myself. I've also witnessed a lot of instrument cables lying in parallel with motor cables, which are high-load AC type applications, and currents being induced in those cables as well. So we want to make sure that any instrument cables or low voltage cables, which include 24-volt DC signals, analog signals, Ethernet, any of the instrument buses, Profibus, DeviceNet, etc., we put those in a separate cable tray, or if we have to put them in the same cable tray, use a metal divider that's grounded, and that will work very well as well. So those are the main ways that we can design in preventing interference on loop-powered signals. Now, obviously, there's going to be some special cases where you may have a very large transformer or something that has a much wider EMI distance. So you want to make sure that you take a close look at where you're installing your cabling, and then take the appropriate measures to make sure that you don't have interference. Let's see. Here's a question. As a young automation engineer, what things should be learned or experienced in 5 years for moving toward automation project management? So This must be someone who is in the automation field and has aspirations. Like I said before, we need to have goals, and the goal of this person is to become a project manager in 5 years. So what you want to do is get as many different project experience as you can. PLC programming, network installation, network design, HMI programming, and then things that aren't at the control level, like data historians or alarm systems or security items. So you want to be involved in as many different types of projects, many different sub-disciplines of automation as you can, because that will prepare you for automation project management. Automation project managers need to have that scope and that breadth of knowledge in order to effectively do their jobs. What I would also suggest is in the Automation Body of Knowledge book that's available from ISA, it goes over all of the different things that an automation engineer should know. Obviously, we had time only to cover 5, which I think are the basic, most important 5, but there are about 56 different areas that an automation engineer should have knowledge about if they're going to have knowledge about everything in automation engineering. So to become an automation project manager, you need to have as many different experiences and many different project experiences as you can. All right, another very good question. What are the most common control loop tuning methods used in industry? How effective is the auto-tuning functionality in PLCs as compared with common industrial tuning practices? So there's really 2 parts here. What are the most common loop tuning methods used in industries? I'll say there's 2, the reaction curve and also something that we call trial and error tuning, which essentially looks at the as-found tuning and then uses those qualitative tuning maps to move the tuning closer to where you want it to be. Where we have the ability to do a bump test, let's say on a new process or processes where we don't have critical flows and during operation time where the operators wouldn't let you do a bump test. We want to do a bump test and get the actual process response. We also might want to do that over several different regimes of the flow or the pressure, whatever you're controlling, in order to get a flavor of whether the process dynamics change at low flow rate versus medium flow rate versus high flow rate. And then for those processes where you can't do a bump test, you would go up to the control loop and just observe the way that it's behaving, try to quantify that or qualify that on the tuning map, and then make adjustments based on the tuning map to get back to the quarter wave dampening or the good control tuning. And then how effective is auto-tuning in PLCs compared with common industrial tuning practices? That's really going to depend on one thing, and that's the stability of your loop. Unfortunately, most auto-tuning programs require less than plus or minus 1% variability in the process variable with that loop in manual mode. In other words, at steady state at one valve output. That's not always easy to get, especially for flow loops. And so it works very well on what I'll call very stable, regular, non-noisy loops. Unfortunately, those are the easiest ones to tune, given the 2 methods that I just talked about. And you'd really like for those auto-tuning programs to work the best on the ones that don't work as well with normal tuning methods. That'd be our noisy flows or ones that have many interactive properties with other loops or do interact with other variables. So there are some more expensive auto-tuning programs that can actually look and pinpoint those interactive process variables. But those that are built into the PLCs aren't quite as advanced as some of the standalone tuning packages, and therefore they're going to have a limitation only in that they need a pretty steady flow in order to do their initial tuning assessment. However, when they are applicable, they work extremely well. So I wouldn't discount them. Just realize that they're not going to work on every single loop that you apply them to. Here's a great question that comes right out of my experience. I've done a lot of batch control and in my past, and it says, what would you recommend as a balance for keeping people in the loop with batch controls changing while not bombarding people with changes? So I think this goes back to project management and actually team dynamics, and changes are always going to occur in a project, and whether it's in a project or after the fact, and changes in batch control could be either an approach for your equipment modules or control modules or in recipes. You're going to have to understand that batch control projects are probably the most difficult to implement and are often underestimated as far as resource time goes because there are going to be a lot of changes. Many batch processes are actually in development at the time that you're actually doing the batch control software work, and there are going to be changes that come up. The CAP model for project management is essential here, where you want to take everything one step at a time and not get ahead of yourself. Don't try to start programming or setting up your area models based on just initial conversations. Make sure that they're based on the approved functional spec or detailed functional spec where you've had time to hash out and distill a lot of the changes that are going to be made. Usually in batch processes, in implementation of batch software, all of those bombardment of changes come because we don't have a full definition of what we want to do. So that's really, really important. All right, let's see what we have here. Next one is there a PLC language that's favored in life sciences and laboratory automation? Well, that's really a tough question because there are so many different options out there that, in fact, the bulk of my experience is in life sciences. In fact, I'm program manager for life sciences, the company I work for now. There are a lot of choices that clients have, and they certainly take advantage of every single one of them. I would say that the biggest three languages that are used in life sciences are function block. A lot of times that will come from the fact that we're doing things such as batch control where we have discrete steps that we follow. Sequential function charts with function blocks is very, very common in the what I'll call the process part of life sciences. In more of the packaging or filling or other more discrete or machine-oriented processes, ladder logic is still probably the most used. Although I'm seeing a lot more structured text in implementations, but for machine control, ladder logic usually is what is chosen. And in the process part, function blocks are heavily used along with sequential function charts. Another very good question. How is the use of wireless transmitters and control loops or other controls? So I think the question is here, do wireless transmitters have a place in control loops or other controls, and how are they being utilized? The answer to that is yes. A lot of people are using wireless, especially for what I'll call out of the boundary limit type applications like tank farms or wastewater systems that are disconnected from the main plant control system. And that just is to save wiring and to save cost of putting all that wiring down over a long distance. One of the things that we thought would overtake PLCs and other DCS control was the PC back in the mid-'80s and 90s. It never happened. Then wireless came along, and it seemed like that was going to be the next best thing, and it never really took over, but it is gaining acceptability, and it is being adopted in those cases where it makes sense. If I'm out in the oil field and have gas transmission lines and stations out in the middle of the desert in Oklahoma or Arizona, I don't necessarily want to have a control room out there with controllers and whatnot. So I'll use telemetry, either using cell or radio frequency to get data from those systems back. On a closer to home note, if you have a tank farm or a loading dock or a wastewater system that's physically 200-300 yards from your main control system, then wireless should be one of those things you look at in order to save wiring costs and installation costs. But again, it's having a somewhat of a labored time of being adopted because of all the security concerns that people have, as well as there are some installation type requirements that some places cannot meet. Let's see. This is a great question about calibration. How do you determine the calibration tolerances for different instrument types, taking into consideration the criticality of the application and the process, e.g. custody transfer, safety instrumented systems, monitoring, control, indication only, as well as test equipment capability and manufacturing tolerance specs? Well, the whole topic of calibration tolerances is really going to depend on the individual company and what their specs are. There are lots of articles that have been written about calibration tolerances from a more generic standpoint or from an industry peer-to-peer standpoint, which are quite interesting, but really you have to figure out what your own tolerances are. I would start at what can the process handle? Is a plus or minus 1% flow variation or deviation acceptable for your process? It may not be for a custody transfer, but it may well be for, let's say, a flow loop that's in chilled water or cooling water service. You need to look at what that particular loop is doing. Is it a pH loop? Are you under regulatory restrictions that you can't put greater than a certain pH out into the outfall? In those cases, you may want a much higher or a tighter tolerance than those instruments that aren't in a regulated service. So really you have to take in advance just the things you listed there: criticality of the operation, whether it's in custody transfer or safety instrumented system. Normally safety instrumented systems are going to use analogs for input only, and there you need to have a fairly tight tolerance, but again, most of the time you're using analog transmitters and SIS systems only to indicate passage of an alarm point. So, you know, if you had a plus or minus 0.5% there on a level, that's probably not a bad thing to do or a bad place to be. So really you have to look at the application, criticality, and when you're into custody transfer or things that are, you know, like test equipment, you need a much tighter tolerance. So basically what you do is you buy a much better instrument in those cases, and you will use the manufacturer's specs and come up with what you feel are the acceptable tolerances for that instrument or class of instruments in your plant. All right, here's a good question. How does an electrical technician work experience count towards CAP work experience requirement? And I'm going to leave that one to answer offline in a more complete way. But all of your experience can count towards CAP work experience as long as it's in a realm of automation. And electrical technician work is going to depend on what exactly you're doing. And so I'll answer that question more fully offline, but I just want to encourage people who are thinking about CAP to you know, start planning ahead, just like this person is, in what the requirements are, knowing what the requirements are. All right. So here's a question. It goes back to where I showed analog devices in parallel. It says, why is a 200K ohm used to read the analog input to the I/O port instead of a 250 ohm resistor? I think the confusion here is on that diagram, which I could probably go back to pretty quickly if I try. You'll find that the analog input is on a 250 ohm resistor, and what I was saying was that the additional devices you may want to put on your loop have to be a very high impedance. And let's see, well, can't get there fast enough. I don't want to spend too much time. We're just about out of time. Yeah, so here we have a 250 ohm resistor, which is for the pressure transmitter. These 200K ohm resistors are for additional devices such as chart recorders or remote displays. And if we put a second or third device on our current loop, we need to make sure it has a very high impedance as to not alter significantly the properties of the current loop. We need 1 to 5 volts at our analog input, and if we put 2 other devices on at 200 k ohms apiece, we're only going to affect the total resistance of the loop by about 0.25%, which is probably okay. So these 250 k ohm 200 k ohm resistors are not for the analog input. They're for additional devices that are powered by the analog loop. All right, I think we're just about out of time. The rest of the questions that weren't answered, and we have dozens of them, and I really appreciate you taking interest in this seminar and asking such great questions. I will answer those, and those will be put out later, as I said, with the transcript of the Q&A session with the on-demand version of this seminar. So being out of time, I'm going to hand the presentation back to Kim for wrap-up. And again, thank you very much.
Okay, thank you, Scott. We are going to be wrapping the webinar up right there. Thank you to our presenter for spending some time with us today, and thank you to all of our audience members for being a part of this webinar event. Please take a minute to complete our survey, which is located behind the survey widget at the bottom of your screen. And as Scott mentioned, you'll be receiving an email from us with a link to the on-demand version of this presentation, where you may also access a PDF of this PowerPoint and a Q&A transcript. Take care, and we'll talk with you soon.